Okay, welcome back from lunch. I'm going to continue with the source code example that we looked at before lunch, which was the person employee. If you have not gotten that one and you're looking for it, it's out on the BHacker website and it's uploaded. It was uploaded along with the video from this morning. And of course, my internet's not going to work now, is it? Here it goes. If you, it was lecture number 10 from this morning. I'm showing this to those people who might not have it and who might want to use it for the second part, because it's helpful sometimes to be able to type in information and see it work. So this is lecture number 10 on 622, and if you open it up and you look under, you'll see the link right here. So it's actually with the video. You'll see the link here. You'll also see it in the source code examples here under miscellaneous examples. It's under lecture 10 source code example. So you'll see it here too. So go ahead and download that if you'd like, and then you can follow along with the examples. So today, right now, we're going to do working with pointers, which is lecture number 7. And I've decided to cover pointers because I had so many questions on pointers. I decided to cover it from scratch. So I'm going to do it right from the beginning because a lot of people are having problems with pointers. You don't understand pointers, there's going to be a big loss in terms of your ability to comprehend some of the other subjects that follow this. So pointing, an exercise in destroying your computer. Okay, so maybe you'll find this entertaining. Who knows? What is it? Well, it's a blue screen of death. It's the nightmare that shows up. Not really. It's just a process that fails because you've written in a memory that it didn't belong to, or you've misused something and it's caused a problem. So let's talk about memory for a second. If we were to look at what memory looks like, it might look like something like this. Probably not. But it's going to look similar. So this is the abstraction we're going to use for the purposes of this lecture. It's a bunch of banks, and here we have the banks are coded 1, 2, 3, 4, 5. All the way down to, it looks like I got 42 little squares going on here. Now memory is not necessarily numbered like that. You'll see a hexadecimal number for the memory. Your MMU keeps track of this for you on your computer. So long story short, you're never going to see anything that looks like this ever. But it's a nice illustrative way of showing you pointers. So the blue is the memory address. That's the 1 through 42. The black is the value that's being stored in there. Memory is actually kind of a funny thing on a computer. There's no need to unstore something. It's a storage area. So we all know memory saves information in RAM. Well, it is RAM. And when we turn the computer off, everything goes away. We turn the computer back on, and we have the ability to load it back up again. So what ends up happening is at any one moment of time, we might have a value stored there, or we might not have anything at all. It depends on what kind of garbage was left over from the last time we used the computer. The operating system isn't going to go through and zero out all the memory, make it all empty for us. Although some operating systems do. In C++, when we work with the memory, we're working with it from the direct operating system, and we're no hope. There's no reason or rhyme to think that anything would have been removed. So we don't get like null, we don't get empty, we don't get to know that nothing is valid there. So that's why this demonstration here is showing you all these values. They just show up. We don't know where they come from. They're garbage values. When we declare an integer, like integer myInt, it goes out and it finds a memory address for us. And this memory address is number 25. So if I were to do something equivalent to that in C++, and now I'm going to go back to my C++ here, I'm going to comment out. I started writing an example already, and then I thought, well, I'll just write it live for you. I'm using the main program. I'm not going to make any instances right now of any of my objects, which are person, employee. Instead, let's just talk about ints. So I'm going to follow along with what's in this lecture here, and I'm going to do an integer myInt. So if I do that and I go integer myInt, I've defined an integer. If I want to know what address this integer's out, I use an ampersand. So if I went like this, I went cout, and I went ampersand, which is the shift 7 on your keyboard. Looks like an and ampersand. myInt. In fact, let's put a little line return at the end. And what's it? End L. There we go. I'm going to print it out, although it's not going to mean anything to me. If I compile and run this, I get a hexadecimal number 0x22FF74. What address is that? Well, in our little picture here, it's 25. So this is a little easier to kind of look at in terms of, and this is what this abstraction we're looking at. And so my int is 25, or x0x something or other, which means out here we're going to call this space my int. And the space is just big enough for an int. Actually, ironically, most of memory is divided out into integer spaces, and it's so many of those int spaces for a float, so many for a double, so many for a character, or portions of ints actually, which is kind of interesting. So what have we done? We declared an int. We've taken up just enough space to hold an int, and we don't know where it is in memory. We don't really care. We never write to 0x77, whatever that number was. We don't really care about that number. Computer just randomly picked it. If I made another one, I'd have another number. But this number stays the same for the life of my program. This is the number that I'm going to be using to represent my int. So what value is stored at the memory location? Well, whatever was there before. Actually, I could print it out. If I print it out, I'm going to get whatever was there before. So I take out the ampersand here. I'm just going to print out my ints. I'm going to get some garbage that appears to the screen because I've declared it, but I haven't initialized it. Look at that, I got the number 2. It's like, wow, that's really nice. What does that mean? Nothing. It's garbage. So over here, out here at my int, I don't know what was in the my int. Number 47. No, number 25. What was in number 25? 42. Mine said 2, so it's not always going to be the same number. It's garbage. So whatever value's at that memory, you can print it out. The value is going to be, oh, it's negative 4717. It won't print. It's garbage. It's a negative number. Mine actually printed. I got lucky, actually. I got something printable. I was expecting to see garbage. So we can copy the value of 42 into that section of memory by going my int is equal to 42. So if I do that out here, underneath here, I'm going to go, okay, my int is equal to 42. And that's how I actually get something meaningful on here, because now when I compile and run it, the 42 shows up on the screen. So the 2, which was garbage, came away, and now I've got 42 that appears on the screen. So now I can, kind of be fairly certain that that's the number I want to be working with. So now this is what I just did a few minutes ago, and I have 42 stored in my memory address for my int. So pointers allow us to get at the address of where the information is located, similar to call forwarding. So we ask the pointer where to go. We go there for the information. So we have the reference and the dereference. So to create a pointer, we use this thing called a reference symbol. Well, that's, what is it, Shift 8 on your keyboard. It's an asterisk. And it follows the format of the data type and then the name, an example, integer PTR. I like to stick the pointer next to the data type. You don't have to, you could stick it next to PTR. So an example, and this is what kind of throws people off in the beginning, is that we'll just leave this alone and we'll come down in here underneath it and we'll create a pointer. So our pointer now is going to be called PTR, so integer PTR. If I did this, what I end up with is just the same thing as my int, not a pointer. I could put the pointer here, and that works. I could put it like that, but that does not look like multiplication, or I could put it like that. And so 3 different locations I could put the pointer in. I like to put it here. Don't ask me why. That's what I like to do. Other people like to put it like that, because then they know. In fact, I do that occasionally too. I mean, I did it right here. No, I didn't. I do it right here. So you can kind of see it doesn't really matter where you put it. It has to show up somewhere between the data type and the name of the variable, and there has to be a space in there. So I like it like that. So I'll leave it like that. So what I did here is I created a reference. This one here allocates a memory cell to be used as my int. This one here does not allocate memory. It's just a reference, which means we have to allocate some memory for it, or we can use something that's already been pre-allocated. So that's why sometimes we use pointers with variables, and sometimes we use them on their own. Because we could do this. We could say, and we did this before in this previous example, we could do PTR is equal to new int. If we did that, what we get is a new int out of it. Or we could say PTR is equal to, well, what's it going to be equal to? Could be equal to the address of my int, but let's go through that in a few minutes. I don't want to skip ahead. Stay on track with what we've been covering so far. So that's called the reference. Used with the variable and the data type creates a reference. So we declare an integer pointer, integer PTR. So now we get the same thing as before. We get a reference. We didn't allocate anything though, but we have a memory space. And the memory space is going to hold a pointer to another memory space. So this guy here, PTR, is the same thing. It's actually kind of similar. It's the same thing, except we didn't allocate. We're not going to use anything here. We're going to point to something else that's going to use this. So we have a pointers at memory address 5. If we printed out the address of the memory address, we're going to get, you know, some hexadecimal number. Same concept as before. So now what we've done, we've created a new variable of type PTR that points to an int. So we haven't initialized the pointer to point to anything yet. So we're going to have it point to my int in a few minutes. So what if we print the pointer out? If we did a cout PTR, we're going to get whatever happens to be what PTR is pointing to. And it's going to be a hexadecimal address, which is going to be nothing. So if we did this here and went to cout PTR, probably going to get some piece of garbage that prints to the screen, but let's take a look here. We get O.35. It's a memory address, just the same way as we print out the address of. So you might want to say that PTR, this is not source code, but it actually is equal to the address of something. So it's the address of something that it's going to be equal to. And because it's holding address. So the reference is holding an address. It's not holding a value. A regular reference variable, excuse me, a value variable holds a value, like an integer value. A pointer is holding an address, memory address. So if we print out PTR, we get a memory address. So how do we get the address of the my int? So that PTR can point to it. Remember, we can still access the values of my int directly. We can say that integer sum integer is equal to my int. And we can always need a pointer to store the address of where my int is located. We don't really need that either, actually. We do not need to store the value of my int for the pointer, just the address. So now what we're going to do is use this address of operator that I used a few minutes ago and have the pointer point to the same address as the integer points to, my int. So we use the address of operator here. And if we use the address of operator, this is what I did a few minutes ago. I printed out the address of my int. But let's just have it equal to my int. If we do that, then we can set them so that my int and PTR are both pointing to the same location. And then we can get to this location, number 25, by the name my int, but we can also get to it by PTR. So we have multiple things pointing to the same address. So if we cout the address of my int, we get number 20. The address of my int, we get 25. It gets printed to the screen. So in here, getting to the pointer, we now need PTR to point to my int. So the code for that is the PTR equals the address of my int. So if I do this, this is the key right here, which isn't really that much. I'll put PTR down here for a second. If I say that once I declare it, here's the other problem people do with pointers. They always worry, oh, is there an asterisk involved in everything associated with a pointer? Only the reference and the dereference. So once I created this is why I like to put the asterisk next to the data type. Once you create it, it's a data type of pointer type, data type altogether in one little package. Then you can just use PTR from then on until you want to dereference it. You'll never reference it more than once. Every time you reference it and use this after the initial reference, it's always called a dereference, which means you're going to follow PTR. So here I'm going to say PTR is going to be equal to the address of my int, which is great. Okay, so now if I print out PTR in here, I'm going to get the address of my int that gets printed out, which should still be the same. So these two items here should be the same. My int's address, or my int's going to print out 45. So if I print out the address of my int and PTR, so this line of code and this line of code are going to print out the identical same thing. They're both going to be the same number. And if I run it, they're both the same number. That's that hexadecimal number that we had to start out with. Why do we want that? Because now we have two things that point to the same memory address. So now I can dereference PTR when I use it and follow PTR and have it equal to something. And then it changes for PTR, but it also changes for my int. As an example, we'll leave this here for a second. If I do this, follow PTR, and I say follow with this, this is integer reference PTR, this is follow PTR, have it equal to 25. Or let's say have it equal to 50. And now I print out PTR. Let's just do them both here. Let's paste it here and paste it here. Now I'm going to print out my int. And I'm going to print out, well, let's just follow PTR. What does that equal? So I could put this asterisk anywhere. I could put it in the middle of a cout command. I could put it out here. I could put it everywhere I want. It means different things in different contexts. Anything from this point forward is a dereference, is what I said before. So follow PTR means follow the address that PTR is holding on to, which is the address of my int, and give me what's there, is what this is going to do. So now I'm going to get 50-50 being printed out because they're both the same. So if I run it this way, I should see two memory addresses, and then I see 50-50, which means my int and PTR both got changed when I did this. So what if I change next? What if I change my int? Okay, well, my int's not going to be equal to 100. My int equals 100. I'll just show you that. Alright, so let's print them out again. If I print them out again, I see 50-50, 100-100. What happened? One's fighting against the other one. You change one, you change the other one changes. You change that one changes. Yeah, they're all changing on me. Well, that's how it's supposed to be. So, people wonder, why do you need that? Well, this is a preliminary kind of step to linked lists. So a linked list is a memory location that points to another memory location that points to another memory location to another memory location, which is very efficient compared to using arrays for stuff. I'm going to talk about arrays after I talk about pointers. But, and I've actually already talked about pointers and arrays so far, so this is a little bit more detail for you. It's handy for juggling memory without having to worry about a structure for you. Creating your own structure, you're making your own memory, and you're having the memory point to each other. And so it makes it a little bit more efficient in terms of what you're doing with it. So let me go back to here. And so this pointer is pointing to the address of my int, which is the address. So before we had this, where we had PTR had 98131, and now my int was stored at number 25 here, and what is this under here? Number 42 is under here, 9. Not quite sure what happened with that. Maybe some roll. Oh, this scrolled or something, or rolled wrapped or something. After the PTR is equal to the address of, well, then now it's equal to 25. So PTR is now equal to 25, and my int is at memory address 25, which is how the linkage is happening, which is why they both put the same information at the same location, because they're both storing the same, they're both pointing to the same memory location. So what would this do? PTR is equal to my int. Well, my int, well, if I did PTR is equal to my int, this is going to be interesting. My int here, storing a value, and my int storing to 100. So if I did this, let's do it underneath here actually. PTR is equal to my int. What's PTR going to be equal to? 100? Because that's what my int's equal to. What's at 100? Huh? Memory address 100? What's at 100? Garbage? If it even exists. Actually, that might cause a crash. I'm hoping to cause a crash before the end of the day. Let's see. Let's print it out now. Let's print out PTR, and then we'll follow PTR. So we're going to print out PTR, probably going to be equal to 100, no? And then we'll follow PTR, and see what that one's equal to. Can't do it. Invalid conversion from int to int. Yeah, because one's a printer, one's not. It can't even do it. It won't even let me do it. This is a bad call. Because PTR is expecting to hold a memory address, not a value. When we give it my int, it's a value, and we're giving it 100 because my int's equal to 100. So we'd had to, in order to make the syntax work, we'd have to do that. If we did that, we're gonna get a problem. You can't have it. You can't have it. You can't make it. You have to be a hexadecimal number. It's wanting to be. It wants to be a memory address. So if we did this, what's going to end up happening? I'll show it to you this way. It's going to be equal. So it's equal to 25. And what's at 25 or 42? Excuse me. It's equal to 42 because my int in this example is equal to 42. It's just scrolled wrapped under here. There's a 42 under here. Well, 42 is over here. It has negative 47. So, so in our case, it would point to 100, and we go to memory address 100. I don't know. I have no idea what's pointing at that. I don't even know what's at that memory address. It's going to be garbage. It's going to be pointing to something we don't really want. Wrong piece of data. So then we get the tricky screens of death that occur at that point. So last thing to learn is how to dereference a pointer, which means how to follow a pointer. Unfortunately, we use the same symbol. They weren't too creative. They used the reference and the dereference symbol all the same. So it's used as well. So if we follow PTR, we end up getting the value of PTR printed out. In this particular case, if we follow PTR, we get negative 4714 because we're going to follow PTR to address 42. So PTR is holding onto a memory address, and the memory address has got negative 4717 in it. Not so good, actually. If we follow PTR here and it's pointing to my int, we get what we got before. We get 25 printed. We get 42 printed to the screen in this case, or in my case, we got 50 or 100 printed to the screen. So here's another example. Again, the blue is the memory address, the black is the values, and the red is the variable name. So let's declare a pointer, and we'll kind of do integer asterisk PTR. No guarantee where it's going to show up. First time we did it, it showed up over here somewhere. Now it's in memory address 10, so it shows up at a different spot. Just randomly selects a memory space. So now we have a integer pointer PTR. Now if we said followed PTR, it's going to print out -6. So if we print that out, we're going to get -6 printed to the screen because we followed PTR. Well, actually 10. We're going to follow PTR. PTR is equal to -6. We're going to go, where's -6 on this board? There is no negative. We're going to get a memory crash is what we're going to get because the memory address doesn't exist. And we're following it. And the value that we're following is -6. So it's not going to print out -6. It's going to follow. We get the blue screen of death that comes out of that. So they don't call it the blue screen of death anymore, I know, but it's an old slide set. Why do I need a pointer? Yeah, good question. Because parameter passing only passes a copy of a function. Can't change the main's variables. It only changes the values that are sent to it. So here's an example. Void cannot change integer x. You send x to the function. What happens? The function stays in the function. Nothing changes. You got to pass the information back out of the function to get it out. So if we run my int and we have 17 and we can't change 17, goes over to the function, then it's whatever happened, x is now equal to 6. It's not changed at all. It's still equal to 6. So nothing happens. We don't get any side effects, and sometimes we want the side effects. Sometimes we want to change it. So if we declare my int, because the parameter passing only passes a copy, this is what's called pass by copy, by the way. Passes a copy of the function. The function can't change the main variables. Function doesn't change it. Kind of safer that way, for the most part. But it's got limited usage. You have to return something out if you want something to happen in that function. When we call the function, we send my int's a value that gets put in as integer x, and then x gets used inside of the function. So. And here's where the copy is made. It's actually made at the function call. So it says integer x in here, and it actually gets copied in. So it makes a local copy, and we have x that's allocated. So we say x is equal to 6. Well, here's x here. X happens to be at memory address number 1. And in my example here, my int's at 7. It's holding the value of 17. That got sent in here, so x is equal to 6. So if we print this x out, it's going to be equal to 6. But we don't change this x. So pass by copy doesn't change the original reference to the variable. So we can print out a copy here, a local copy, where we can go cout x. So this x is going to print out differently than this x, because this x is going to be equal to 6 over here. But my int that got passed in here is actually equal to 17. So because parameter passing only passes a copy to the function, it can't change the main variables. Main's variables never get changed. So x is gone and leaves to be garbage collected. Leaves to be gone. So return to main, we print 17. So because the parameter passing only changed it within the function, when we left the function, what's happened, the function stayed in the function. When we went back to main and we printed out my int didn't get changed. Didn't get changed at all. Now with pointers, we can create the same function and have it equal to a pointer value. So it accepts a pointer. If it accepts a pointer, then we send it a pointer. What's a pointer? It's a memory address. Pointers hold memory addresses. So here we have integer asterisk x, and this is because it's a pointer value. And now we're going to follow x and have it equal to 6. Well, what's x going to be? We're going to say that integer pointer ptr. So we get like kinds here. It's a memory address. It's going to be equal to the address of my int, which is out here somewhere in memory. And can change, we're going to send it the pointer value. So it's expecting a pointer, so we send it a pointer. So getting this syntax here to match this syntax here is key. So if we put it out here, let's just create a couple functions. We'll create some more functions here, some changes. So I'll put the functions up here above main here. I'm going to call it void my function, or what is it, can change. I'll just here can change. So we're going to put in here, it's going to take an integer value, and it's going to be integer, I'm going to just call it I. Yeah, we'll call it I in here. So anything we do, if we have a pointer, this is the same as if we were inside of main. So we can follow I and have it equal to 10. Or let's have it equal to 22 so we can see the difference here. And it doesn't do anything. It's just, we're just going to change the value of I. What's going to be the value of I? Well, we're going to do, here I'm going to call this change me. Change me. So now I'm going to use a function to change the value rather than an assignment expression. So I'm going to send change me pointer ptr. So in here, let's see, follow pointer, have it equal to 50. This is the one I don't like. We'll run change me. Change me and send it to ptr, because ptr is a pointer. And now we don't need this one anymore. We don't need the address. And then we'll print out ptr. We'll follow ptr and print it out when we get out of the function. So now we had 50, 50, 100, 100. Now we got 22. after we ran this function call, and the function call took PTR and sent it up here into this function and changed it, followed I and changed it to 22. So now if we just print out, let's print out my int, we're going to get 22 as well. So let's just do it this way. Everything that is, everything that's basically, we got 22, 22. We got my int changed too, because we had my int, PTR is pointing to the address of my int, which is where the memory actually is stored. So we sent a reference. This is pass by reference. This is a pass by reference. Because, and this is pass by value actually. This is a reference here actually too. But this one here is a pass by reference because we're sending a pointer. And so we don't have to return anything with a pass by reference. So we don't have to send to there, allocate memory, return it back to the main. Time consuming, slow. So in this context, we're doing this because it's supposed to be faster. It speeds up the process a little bit. So I just demonstrated that function to you so you don't have to continue with this one. So I could declare my int up here, which is what we did, and we sent it to the function, and we passed it by here. We passed a copy of PTR to the function, and the function inside of the function, it changed it permanently for us. Can we do the same thing with an object? Sure. So out here, for example, we have, because why do we want to send an object to a function and return the object back from the function, or return the information back from the function, and then copy the stuff into the object? Too time consuming. So this one here says an integer. Well, couldn't this be, what do we have down here? Employees or something? Employee. Employee. And then we change it here, so we're going to, let me make this an employee E. We send the employee to it, because isn't this the same thing down here? We created an employee barb. So I have to take this one out because this one's not going to work. Actually, let's just do this. Cut. And that's going to be equal to a new employee. So then now we can just say change me, and send it barb. And then if we change it in here, wouldn't this be like E dot something? No, E dot do something else. Let's see what happens here. We'll just leave the body empty right now. So person age constructor happened, and then employee IA constructor happened. What do you mean? We made that instance of the object, and then we ran it, but we didn't do anything inside of it. I took the body of change me out. But here we're passing the object, so the object is going to permanently change. Whatever we wanted to do to that object is going to change inside of this function. So we don't actually have to send anything back. These objects are big, they have a lot of information in them. We're just going to change what's in for the object, and so it creates a pass by reference that allows us to change whatever's in that object. So we can, you know, change the, and in fact you might notice something else here too. So when we run the methods on these objects here, under employee barb, we ran employee barb, and then we said barb, and then we used the special symbol here for the dot resolution operator. We said, well, what are we going to do in here? Well, we're going to run the, what do we have in here? Get, do we have set age or something? Let's see. Set age. Let's run this get age. Well, let's set the age. Set age to, we'll make her 21. We have the special thing that we use here. Well, couldn't we just do this then here? Copy. Paste. Let's take this one, make it 99. And we're going to get barb undeclared. Oh, probably because barb is undeclared. We're going to call it E over here. The instance of this object is called E up here. So now we have, well, I didn't do anything. I didn't print anything to the screen, but we're not following it anymore. We're just running the same code that we would run down here. We're running it in the method, excuse me, in the function that we created. So you might think that this syntax here is the replacement of having to do this. Follow E. Have it. So this arrow is to follow. So in the object's an instance that is created from dynamic memory, instead of the dot we use the arrow. Well, that's why. It's the equivalent to not having to do this. Why they did it that way, I don't know. Because we could do this, follow E, and then run dot set age. That's going to give me a syntax error. That's going to give me a syntax error. Should give me a syntax error. Yeah, I want it to give me a syntax error because it's going to say that set age has not been declared because it doesn't know that it's a method of this object, because we're not treating it like an object, we're treating it like a pointer now. We're going to the memory address. So follow the memory address of E. We could still print out the memory address though. We could just still use the ampersand of E printed out. So if we did cout. I wonder if this would actually work. The address of E. Let's see if this actually works. Yeah, it prints it out. 0.22FEFO, which is interesting because it's a different address. It should be a different address. It's E referenced in here. But we could say, well, it's going to be the same thing. It's a memory address. So we can't follow the memory address and set the age. So instead we use the same syntax that we're familiar with before and we set the age. And so down here we could you know, print out the age or something. We don't necessarily need this one in here because we're setting it in the change me function. So we could have a method, excuse me, a function where we created objects and we sent the objects to the function and we set the age and we set the name and everything in the function if we wanted to, which is kind of different. You could use the methods inside the object to do the same thing. There's no reason why you'd want to pass it to a function, but you can if you want to. So just shows you a little bit more examples with that. So here we follow X. We're going to use a different syntax for the objects. And so if we follow X or follow PTR, we're both pointing to the same memory address, which is why, because this X up here is pointing to the same memory address as the PTR, which is pointing to my ints in this particular case. So changes whenever X is pointing to. So whatever X happens to be pointing to will change. So we can make a generic function actually that kind of works with all objects that we send it. We just call it an object. And then we can have something, you know, we can send a person to a function. We can send an employee to a function that takes person by casting the employee to a person. Send it to the object. The object type has to be the same. As an example, when we went back up to this example, oops, not this one. Clicked on the wrong thing. When we come back over here, if this one was employee, let's say this one was person, but we only have Barb. Barb's an employee, so we could cast Barb to a person, send it to the method, to the function if we wanted to. And then we treat it like a employee, as long as we were compatible with what we were sending it. So here we could cast Barb as a person, send Barb as a person Barb. I don't know if that's going to work or not because of the syntax. No, it's not going to work. I'd have to make another. I'd have to make a person employee, like, you know, person, my person. It's going to be equal to person Barb, and then send my person here. If I could spell my person right, there we go. My person. So I'm sending my, oops, I'm still going to have a problem here. Person, invalid type conversion, employee, it's an employee. We'll leave it alone. Anyway, long story short, because I didn't create the person that had the right constructor. So long story short, we have to object, that's the reason why we're going to cast an object in the hierarchy to make it compatible with whatever we're expecting in the object we're going to send it to. And that gets a little tricky. So you can make this one here, we'll put it back to employee. I don't have the complete person created because I ran this constructor. If I just did a regular person, I can cast a regular person to an employee that ran the regular person constructor back to a person of that same type because all the data is populated. Casting is a bit risky as well because we want to make sure we have the right, whoops, this is Barb. We want to make sure we have the right data that is assigned and created for the object. Okay, good. Alright, so moving right along. We have a change in here, seen as a change in there. Interesting note, at this point, these two statements will print out the same thing. If we print out, and we saw this already as well, they follow PTR and print out my int, we get the same thing because they're both pointing to the same memory address. So to understand the pointers, you need to understand memory. The address of is the secret to all of it, and we can create and dereference with the reference here. And passing a pointer to a function can change and make changes to the main, which is why we're doing it. So let's take a look at lists, linked lists, stacks, and queues. We're moving right, unless we have questions on pointers. That was our second run through on the pointer concept. It's actually not as hard as people take it to be, and it does. You know, the only way you can really get around to the concept of a pointer is to practice it, because then you'll see it come together for you. Outside of you can't learn it from listening to me or from reading a book. You pretty much have to start using pointers. And the best way to start using pointers actually is with objects. So, as I mentioned before, some of the problems with pointers and objects is this classic scenario here before I start in with the nodes and the linked list. I'm starting with this example that I started creating before the lunch break was over. If this is the classic example that we get when we create pointers with objects, is that here we have person peep, and peep is going to be equal to a new person. And then we have person peep2, which equals to a new person. And then peep2 is equal to peep. Well, one object now equal to the other object. What happened to what happened to the memory here that we created for peep2? It's garbage. There's no way of getting at it. We can do the same thing without objects too. We can say, as an example, let's create a memory link here. I'll put it at the bottom here. Not to that we want to create so many memory leaks and stuff here. I think I'm going to leave this alone. I'll put it right up above here. So if I said integer PTR2, and that one, I went over here and I said, well, I can say PTR2 is equal to, well, let's see, let's just go this way here. Let's allocate something. Equals new int. And then PTR2 is going to be equal to the address of, let's say, my int. I just created another, because every time I do a new, I need to do a delete that goes along with that. Let me just make sure that this code doesn't have any spelling errors in it. No, we're good. So by saying PTR2 is equal to new int, and then taking PTR2 and having it equal to the address of my int, or better yet, PTR2 could equal PTR. I could do this as well. I can go PTR2 is equal to PTR, because they're both pointers, and if they're both pointers, then they should be able to be assigned to each other. Haven't really created a memory leak though with that one. Well, I have with PTR2. So if I said PTR, if you remember up here I never said new. I said integer my int, and then I said integer pointer PTR, and I had pointer equal to the address of my int. I never went new. So just like we go new here, new person, we can do new float, new double, new anything we want. When we go new, we actually allocate a space, but we're not putting a name on the space. We just have a pointer to that space. So this operation here returns a memory address. So PTR2 is now equal to this memory address of this new integer. So if I wanted to, I can go like, say for example, let's try some floats. Float asterisk A is equal to new floats. And float asterisk B is equal to new floats. So I've got some new floats. And then I can follow floats and I put the values on it. But as soon as I start doing this, A is equal to B, then I'm going to have a problem, because I'm going to run into another memory leak. So there's no reason why I have to do so many news. So that's why people break this out. And that's why you'll see this a lot. You'll see floats. Here, I will just break it out this way. Put a semicolon there, and then go A is equal to new floats. And then you'll put a semicolon here, and you go B is equal to new floats. And then you've actually explicitly created the floats to go along with to allocate to the reference. So now instead, this would be equivalent to, let's say, A. Oops, let's do it this way. B is equal to the address of A, which works too. Or actually, B is going to be equal to A. It would actually be equal to the same new float over here. So we wouldn't have to do this line here. We go float B. Actually, I'd probably just do this here. Is equal to A. Now I have two pointers pointing to the same memory address, and it's the new float that I created with A. So I have the ability to create memory when I want to use memory, and don't create memory when I don't want to use memory. So let me tell you how to link memory together, which is kind of interesting. So I am going to leave this one as is and add a new structure in here. And the structure that I'm going to put in here is going to be called a node, because I want to talk about linked lists right now. So I'm going to leave this as is and come under here and declare a structure up here. I'll put it at the top here. And I'm going to call this one here structure node, which is like a class, but I don't really need to make a class. So a lot of people will make a structure for a linked list because we just want to hold something. I want to make it, what I'm going to demonstrate to you is the concept of a linked list, and then I'll show you the theory on it. And then we can see, maybe we can put the pieces together here. So a node is like a tree node. It's like a branch. Well, a node is a node. It's a unit, and the nodes all connect together, and we create a list out of this node. And the way we create the list is the reason why we want to do this is because we want it to grow dynamically. So another good use of pointers is the fact that you can allocate, deallocate, allocate. It's all dynamic. It's all controlled by the programmer. We don't have to worry about there being a known structure for this or a known anything. Actually, we can kind of create our own. So this node is going to be a node of integers. So I'm going to put a piece of data in each node. And then I'm also going to have a pointer to another node. So and I'm going to call this pointer next. And next is going to be a node. So then I'm going to use the data type node, and this is going to be a pointer. I'm going to call it next. So what we get is this concept of a node. And the node is a structure, complex data type, holds two pieces of information. The information it's holding is a piece of data, which is going to be an integer type, and then a pointer to another node. So we could follow the nodes and print out what's at each location, and we can link the nodes together. It goes, you know, in that expression, you're only as strong as your weakest link. One of the nexes, one of these links here, this is the link here, one of these links gets lost, which is why they call this a linked list. One of the linked lists gets assigned incorrectly, you've lost the most of the list for the most part, because the list isn't gonna, you're not gonna be able to find the next item in the list because it's gonna be stuck. So I can create an item here. So I'm going to kind of keep this here and then go down the main. I'll put this at the top of the main here. Let me get rid of my couts actually, because I don't want miscellaneous stuff to be printing to the screen so we can see what's going on here. So I'm going to comment out my stuff that goes printed to the screen. Yep, nothing else got printed down there. So now when I run it, nothing should happen. Should get a blank screen. Whoops, no we don't. We have stuff happening. What do we have happening here? Did I not compile it? Let's compile it. Didn't I just blank everything out? Oh, because the node. Alright, the objects that are being created are printing stuff to the screen. Okay, so let me get rid of these objects. Don't really need the objects anymore either. Okay, I've got rid of the objects. Now I'm expecting a screen to be blank. Yes, good. We have a clean slate to start out with here. Alright, so I'm going to create a node here by the same kind of syntax I used to create with a node. So we can create a node that's a pointer that's going to reference a node that we're going to create. So we can say a node is going to be equal to new node. So we usually start out with something like a head as an example, a head node. So I can just say, you know, and this is going to be a node. It's going to be a node format because it's a structure. So I can say node and call it head. And then I can create like an item. So the head is going to be like a pointer that's going to point to the start of the list. And actually I could create an item for head, or I could just leave head and have head point to the first item. So I could create a first item, which is going to be another node. Or I can just go like this and say, well, head, isn't head going to be equal to a new node? So I got head now equal to a new node. So we're going to make head equal to a new node. Just a simple linked list example. And then if I do that, let's make sure we got compilable code here. No, we got node must have been declared. Well, maybe I should do this here with a capital N. There we go. Isn't that the same as what we've done so far with the employees and the people? It is. So what we're going to do next, then we'll say, well, what's this node going to carry? It's going to carry a value, and let's call it an integer value because we created it with an integer data. So then underneath it, I'm going to go, well, it's called head, right? Head is equal to new node, so I'm going to go head.data. Well, I can't use the dot because I got a pointer going on. I'm going to use that symbol instead, and I'm going to go data is equal to, let's call this one 1. And then what's next going to be equal to? Null. It's not going to be equal to anything. It's our first item in the list. So I'm going to go then head, oops, next is going to be equal to, oops, head.next. It's going to be equal to null. Let's see if I can do that one correctly. Is it nil or null? N-U-L? First use caps. Let's try caps. I might have to, oops, if I compile it. Okay, we're good. I was going to say I might have to include another include for that, but we're good. Alright, so what do we got here? We got a new node, just like this, just like the person, just like the employee, but I created a structure. Well, what's the difference here? I can just do this if you guys like class better. Class node. Same thing works. It should compile just fine. Class and a structure are, let's see, data is private. Oh, because it's private by default. Hold on a second. Let's make it public. By default, the data in a class is private. So if I make it public, then we got compilable code. I'll just leave it like a class right now, actually, because then we can add functionality to it. So I'm going to indent it a little bit so it looks more like a class. Okay, so we made a new node, called it head. It's just the name we're going to do for it. Okay, so let's create another node. So if we create another node, then we're going to go the same process all over again, except for this new node is going to be attached. So instead of the next being to null, next is going to be equal to this new node that we're going to create instead. So we can actually create like a dozen nodes if we wanted to and connect them all together all in one shot by going, instead of this new node is equal to, we can actually create a loop for this too. Instead of this new node is equal to null, we can actually have the new node, head.next, because head.next is another pointer, right? Just like head is a pointer. This one could be equal to a new node. And then we got another node. And then we take the new node. But it's hard to kind of conceptualize that unless you put it into a loop and you just create a dozen nodes over and over again. But the theory is, again, we're going to create another node. So some people actually do this. They go, well, node, let's just create another one, right? And we'll just call this one current. We're going to have a current node. And then we're going to have head next equal to current. And then we're going to assembly line them together. We're going to attach them by the next. So this is This is the link right here that's going to link all these nodes together. So if we have node current, all right, so node current, and then we're going to go say, let's say current then is going to be equal to, we're going to have a lot of repeat here in the code. I could cut and paste it, but current is equal to new node. What are we going to have current is equal to? Current dot current data. Data is going to be equal to 2. This is item number 2, right? And then we're going to have, let's say, for example, oh, I don't know, head, oops, excuse me, current, next, and then let's put it, let's say have it equal to, don't we still have a head? We do. So we can have it equal to head. Isn't it a pointer? And a pointer and a pointer equals a pointer. So now we got current next is going to be equal to head. So if we do that, then let's just make sure I haven't introduced any typos, and I haven't. Then when we print it out, we got current next is equal to head. We put it between the head and the next is actually pointing to the current. So although we're calling it current, maybe we should have called it next or something. I don't know, another word for it. Could have called it another. It doesn't really matter what we call these pointers. So we have the head, and then we have current next is equal to head. Well, couldn't we just flip it around and say head next is equal to current? Long story short, are we going to put it before the first node, or are we going to put it after the first node? It determines the order that we're going to build the list in. If the list head is going to point backwards, or is the head going to point forwards? So most people would actually do this. They'd go head next is going to be equal to current. If you go head next is equal to current, then we're going to have 1, 2. If we go current next is going to be equal to the head, then we're going to have 2, 1 when we print it out. So you could play around with that actually, but head next, because we still have a pointer to head. That's that node we just created, and it's still pointing to head. So if we point to head and we go head next is going to be equal to current. Then we have 1, 2, and then we continue the process 3, 4, 5. So if we print out at this point, just so you can see conceptually here, if you print C out, we're going to print out the data, so we'll follow it. We'll just go head data, and then oops. And then we'll go current data, end line. There we go. Let's see, give or take a few spelling errors and issues. I got 1, 2. So it's giving me my order that I've got, but I'm not going to do it this way. Instead, what I'm going to do is create a loop and then print out the head and go next, next, next. Because all I need to do is follow the head, follow the nexus. So I start with the first node, and then I go next, second node, next, third node, next, next. That's the concept of the linked list in a nutshell. So let's take a look at the theory behind this. What I want to do is kind of show you the concept, and then we'll kind of work backwards, and we'll get to that point again, and then we'll take it a little step further. So the list is a collection of data elements in an array structure. From any given elements in the array, the previous or the next items can be located by moving to adjacent memory locations. This is what they call a singly linked list, because there's one single list. What about a previous? If we had a previous, then the previous would point the opposite direction. So the next here, head next is equal to current. We could set the current next, which we haven't set next, is equal to null. So if we wanted to finish this, it would be current next is equal to null. And then we would, if we wanted to, we could build it in any order we want. But we could actually set a previous. So if we set a previous up here, if we wanted to make this one into a doubly linked list, which means it can be read forwards and backwards, so we're going to go next, or we're going to go previous, then we would go node previous, and then we would set a previous, head previous, which is going to, well, there's nothing. The previous here would be head if it was the first one, or the null if it's not, there's nothing previous to it. But I'm not going to complicate things right now, but think of this as a singly linked list as an example. I'm going to show you some pre-built samples in a few minutes actually that has it all put together so I don't have to type it. So the linked list here is the collection of data elements where you have a memory location, and it's only recorded by a pointer from a previous memory location. So the elements themselves are pointing to each other, which are connecting them together. And it can be relied upon because essentially, you know, well, it's only as strong as its weakest link, but it grows to any number. So here's your list that might be an array of 5 items, 5 integers, and then the linked list are the items held together by the nexes or the previous's, depending upon how we're going to configure it. So they're just sequences of data links together in memory, and each element in the list is made up of the data plus the pointer to the next element. So the node is the common name. Don't have to call it a node. You could call it something else. And it's used associated with the nexes essentially, and there's many kilobytes of data that might be associated with it. In fact, you can have like car parts, you could have inventory item, you could have any structure or any class that you wanted to. In fact, we can link all the students together. All we have to do is put a pointer to a student inside the student class, or the person or the employee. Put a link in there to another employee, and all the employees can keep track of each other, or all the persons can keep track to each other. It's just a link. It's just a pointer to another object of the same type. And if you follow the pointer to the next location and then follow that pointer to the next location, you can possibly see what the concept is. That's all it is. It's a chain. It's only as good as this link is link. So you can be erased or corrupted a node in the middle of the list, then you pretty much have lost some of the lists. So we have this concept of the queue, which is a first in, first out, versus a stack, which is a last in, first out. So this concept is keeping track of, you know, what order we're putting things into. So queues can be of 2 types, a first in, first out. So imagine you are waiting in a line at a bank, and you're going to create a linked list to represent the people who are waiting in line at the bank. Well, the first person who comes in is going to be the first person who's going to be taken out of the line. That's the first in, first out. Second person is going to be the second person. Third person is going to be the third person. If you're designing, that's a queue. That's a first in, first out, which is determining the order. So I've shown you how to put things into the queue or into a linked list. And a queue and a stack is nothing more than a named list that follows certain characteristics. It's a common data structure. And we might actually be teaching data structures next term, but that class is going to be an online class next term, and I believe I'll be teaching it too. So I was telling you at lunch. So it might be an interesting class to take online for the first class. So now everyone was like, online? What is she talking about? It got quiet in here, didn't it? Yes, IT will have online classes starting next term. International students can take 1 class, 1 online class. It's a replacement for a weekend class. Instead of sitting here 3 weekends, you take it online. Wow. 1 class per your degree program for international students as it starts right now. As the program develops, it might turn into more, who knows, but for the first term it's going to be 1, so you can take 1 class. Well, there's only 1 class going to be offered, though, of each department for the first term, and then the next term we'll have more classes being offered. But anyway, what was I talking about? Oh yeah, I might teach data structures online. So if you're interested in data structures, there's an opportunity, perhaps you might be able to take it. Anyway, it's next semester, in another month and a half from now. And the EMS has currently been going under transition to support the online classes. So there's new announcement features, new bulletin, forum discussion kind of features and stuff. So you can talk online with your friends and stuff. But yeah. All right, back to first in, first out. It's a queue, and then we have the last in, first out, which is a stack structure. So last in, first out queue, first in, first out queue. Well, okay, this is but both referring to queues that can be described in both directions. The last one in terms of the lines, the last item in the queue is the first one out. A stack of paper, as an example. It's calling it a queue. It's really called a stack. Imagine plates in a dishwasher, or excuse me, being unloaded from a dishwasher into a cabinet for a stack. You take a plate out, you put it on the shelf, empty shelf. You take another plate, you put it on top of that one. You take another plate, you put it on top of that one. You take another plate, you put it on top of that one. The first one you put in is the last one you're going to take out. So the first one you're going to take out is the last one you put in, which means all the ones on the bottom get dusty and dirty, and it lets you rotate the stack. And then usually the ones on the top are the ones that are all broken and stuff too, because people use them more often. So you pull it out of the dishwasher, you're going to use it, it's going to go back into the dishwasher, you're going to pull it out again, or you're going to, whatever, manual dishwasher, mechanical one, whatever. Long story short, that's a stack of plates, if you want to remember that. So you can build the linked list in both orders. So they, in this lecture set, they're all following a last in is the first out. They're all following a stack format. So we're going to build all of these linked lists in the lecture with a last in, first out queue. But we could have made them all a first in, first out. And I showed you before, it's just a matter of how you're going to create the nexus. So as an exercise, you could turn these examples around and put them in the opposite order. So here's what I was talking about before, the structure node that I created for you. And I'm going to use the one in my example instead. And a list element, well, that's a type-defined list element. It's really a float. So this could be float value. I used an integer data. You could call it value. You could call it anything you want. And then, but here's the other thing here is you have the node next. So it's another pointer in there. So there's basic 4 functions of a linked list. You can actually create a class to represent the list and then put the nodes inside of the list. Or you can create the nodes and just have the nodes be the list. The only problem is once you end up with the list, then you want to do some stuff on the list. Well, what do you want to do on the list? Well, you might want to sort the list, count the list. If the nodes are inside of a list, if there are nodes that are created as instances that belong to a list, and the list is a separate class in itself, then you can build it from 2 different levels of abstraction. You can build list functionality, and then you can build node functionality. So it makes it a little bit more user-friendly. So here's a diagram. Once you've set up the class members, the functions, and you created main in the program, then you start creating stuff. So here's our first, or I called it head. It leads to a node. The node's holding a value. I put value as 1 in my nodes. And then the next, which is going to be pointing to another pointer, another piece of memory that's going to have value 2, that's going to have value 3. The next that points to null is the last node in the list. So if I said head is equal to null, I pretty much emptied out my list, and I've created a bunch of garbage in the meantime, because that list is going to be empty at that point. So we have an easier example I'm going to show you right now, actually. And I'm going to download it. Oops, it's another pointer example. I'm going to take this and I need to bring it into the ITU class, actually. I have it at a different location. Let's see if I can remember where it's at here. Yeah, don't worry about this location. I will put this file underneath the video when I record it, so we'll see it. Hold on one second. I want to go into this one. Linked lists. I got super easy list. Let's download super easy list. They're pre-made for me, so they're my examples, but I don't have to type them now. So I got one that's called super easy, and I'll include this with and I'll put them in the examples folder for our class. And then I got easy list. So let's start with the super easy. I'm going to close this one for a second. Save it. Yeah, why not? Save, yes. Double click on super easy. We'll see what's going on with super easy. Super easy. Here we go. So now I don't have to retype. So you might notice here I put the pointer over here. That's the first thing that catches my eyes, actually, because I like it here. But I put it over here just to show you that you can put it over there. So I got structure. I'm going to use a structure for it. And I have integer x. I could have called it value. Could have called it data. But I just called it x. And so, and we also have a node. It's a lowercase node, so I don't have to worry about it this time. So node next. So what we're going to do here is we're going to create the first node. So the first node in the list, here's node head. And then a way of keeping track of the other nodes, as we did before, we did node current. I just showed you, I started showing you in the previous example. So we're going to say head is equal to new node, sets it to actually point to something. It's going to point to this piece of memory here called a new node. It's a new node. It's going to create a new node for us. And then now the head next is equal to null. Same thing I did in the previous example. And then we set the head x is to 12. Started out with 12. So I'm going to start with a value of 12. So the value that's going to be stored ahead. Now this is going to show you a design flaw because the head is storing a number, which means as soon as we move the head around, or if we add something to it, rotate the head, then we're going to need to basically change the numbers around, change the order around. So let's add an item to the end of the list. So if, and we have here current is equal to head. So the current node is the head node because we only have one node. We keep moving current one over, one over, one over, then we know where we're at. It's a pointer that keeps track of the nodes for us. Think of it that way. So here's the current. It's going to be equal to head. So if current doesn't equal null, if current equals to null, then we have an empty list. Nobody's in the list. So we're going to assume we don't have an empty list. While the current, and this is how we're going to loop it, while the current next doesn't equal null, which means we have items in there, then current is equal to current next. This is our entire loop here. That puts us to the end of the list because it's going to go current next, current next, current next. And we're going to print out the list in a few minutes further down. And you'll see how you can visit each list node, print out the data, go to the next one, go to the next one. So this is the whole key to the iteration, not that complicated. So this is what I did before actually. I said the current next is equal to new node. Well, we can do the current next is equal to new node, or we could just create current. I did it in a slightly different order a few minutes ago. Current is equal to current next. So now current is going to be then equal to the next one. And then current next is equal to null because we're at the end of the list. And then x is going to be equal to 24. So it prevents us from going any further in the list, but if we say that the next is equal to null. And then we're going to create another node. So we're creating nodes manually again. And we're creating it at the beginning of the item at the beginning. So we're going to take and say, well, if current doesn't equal null, and it doesn't, we're going to go to the end of the list again. If we go to the end of the list again, we say while current next doesn't equal null, current equals current next, current is equal to current next, because we're checking for a null. As soon as there's a null, we're going to stop, because there's no current next. So we go current next, current next, current next, oh, current null, then we're done, because the while loop's going to break. Then we're going to do the same. This is the same code all over again. It's done this way so it makes it a little bit easier. I don't know, I could say it 3 times. Probably could create a loop for this instead. So current next is equal to new node. So current next is equal to new node. Instead of current next is equal to null, now current next is equal to a new node. And now current is equal to current next. So we moved it over one. So current next is a pointer. Doesn't point to anything yet, pointing to null. Well, now it's going to be equal to new node. But then the new node, its next, is going to be equal to null. And then, well, let's make the value equal to 36. So the current x is equal to 36. So then print the list out. So how do you print the list out? Well, make sure that there's a place to start with. So you go, well, if you're basically going to say current is equal to head. So you're going to move current back to the head because you don't need current to keep track of each one of the nodes. So a common mistake new students do when they do this is they make a pointer for each one. they make a pointer reference for each one of those nodes. So you have item 1, item 2, item 3, item 4. That's a lot of references you don't need. All you need are 2. You need a head and you need a current. Current and head start together, and then current moves over, current moves over, current moves over. You want to go through the list? Move it like a typewriter. Move the current back up to the head and start over again. So current just goes like this constantly. Goes this way, goes this way. So we're going to put it back at the beginning. So current is equal to head, which means they're both pointing to the same memory address. Head never moves. If head moves, you got an issue because you're going to forget where the beginning of the list is. Current can move all at once, which is why you need 2 pointers. So if current equals null, you got an empty list. You know, because current is empty. So it's not going to be empty. So while current next doesn't equal null, which means you haven't hit the end of the list, see out current x, which is the item that's going to be held for current. And then current is going to be equal to current next, which is going to move it over 1. Now current is going to be equal to current next. Move it over 1, move it over 1. So this is the line that's making you go through the list. So it's allowing you as a pointer to go through each one of the list items. So, and then print out current x when you hit the end, because you're going to stop on null. So print out the last one. Now if we wanted to add an item to the list, we go current is equal to head. And then current is equal to new node. Create another new node. Current next is going to be equal to the head next. This is what I did actually in the last example. Head next is equal to current. And then current x is equal to head x. Well, we have to shift the head over is what the problem is. And then head x is going to be equal to 48. We added it in. Now with 1 added to the start, we're just going to print it out again. So if we run this piece of code sample, we see the basic functionality of 12, 24, 36 being added in. And then I printed out a cout sign that said now let's add 1 to the start. So we have 48, 12, 24, 36. So this is first in, depends on how we read it actually, there's no way of telling it, but it's an ordered list sequentially, and we had to move the head over, so head was 12, and then head turned into the 48 one, because we're keeping an item. So if you keep an item for head, if you have head point to an item and you actually store an item on the head, because normally you'd have head as a pointer going to a node. A node would be current. But if you make a node for head and have head pointing to it, you got to keep switching the values. Every time you add something in at the beginning of the list, you got to move the head over. Which means if the value, otherwise you get the wrong order of the list. If I comment out the code to move the head over, the new node's the head node now. If I don't do this stuff here, then I'll be putting it in the wrong order. So because head's going to be here and the new node's going to be here, instead of me moving the new node. It just basically moved the new node over. So you could possibly see by this simple illustration that linked list is not as hard as people think it is actually. It's just a bunch of pointers. And don't worry, I have more pointer stuff to show you. But I want to introduce, because unless you realize what you need these pointers for, you don't bother really learning them, and then you go, I never thought I needed to use a pointer for anything. What about a linked list? Definitely need a pointer for that one. That one was super easy. Let's try easy. Don't worry, I will include these as well on the website. So again, we have a list node. And list node has an integer data, and it has list node next. All the nodes look the same. And so in main, we got list node head is equal to null, created the head. This one actually does not allocate a piece of node, does not allocate anything for the head. It just keeps an extra head pointer and points it to the start of the list. So we don't store any data under there. So read in integers from the input until a non-integer is encountered, ignoring the white spaces. So while this is what we're going to do here, we're going to create a list automation. So we're going to create all the nodes from a list of numbers that the user is going to type in. Instead of doing them one by one, see how short this line of code is? This program is real short. The one that said super easy on it is much longer because we didn't create a loop for it. We just, no loop, we just did 1 node, 2 node, 3 node, 4 kind of thing. So, alright, so here's main. Main creates the head. So usually you're going to create a head. And then we have integer k that's going to represent the input from the user. So the cin, we're going to cin a bunch of numbers. We're going to input until a non-integer is created. And then we're going to create list nodes for it. So while cin doesn't, while we'll get some input, list node, new node is going to be equal to new list node. So these are, list node is the same thing as the node in the previous example. So we're going to call this one new node. So it's going to be equal to the list node. New node data is equal to k. That's the number we're typing in. New node next is going to be equal to head. Head is going to be equal to new node. And then we keep coming in. We keep put them in, put them in, put them in. So we're going to loop it in. This works because we keep pushing them over, pushing them over, pushing them over. So it builds it automatically for us. And to print out the list, we're going to say for list load current is equal to head. Current doesn't equal null. Current is equal to current next. Isn't that the same as integer I is less than 10, I plus plus? So it's like current is equal to current next is like I plus plus. Because we're going to go current, next, current, next, current, next. What we're going to do is going to print out the data that's in the nodes, and then we're going to end. I think I'm going to have to put like a get character down the bottom of this one, I think, in order to run it. Otherwise it's going to go away. So let's go here, get character. Some of these examples, in fact, let me do this here, and that way I'll just put a couple of them in there. So if I run this example, it's going to want a bunch of numbers. So I'm going to put 1. It gets rid of white spaces and stuff. So it's 2, 3, 4, 5. And then I'll put A. Oops, and it went away. Hold on a second. The input buffer gets filled in this environment, so and that seems kind of stupid, but I have to put all those in there. 1, 2, 3, 4. It's for each one. How many did I put in? Well, it's for each one of the returns I put in. E. 4, 3, 2, 1. Okay, so if you can see this, here I'll do it again, for those people who may have missed it. If I run it, I can put in 1, 2, 3, 4, 5, because I have those 5 returns I'm putting in. I put 1, 2, 3, 4, 5, and then I'll put in a non-integer character. So I'll put in a G. And now I have 5, 4, 3, 2, 1 being printed out, which is my list that I put in, which was the 1, 2, 3, 4. But it's all being put in front of the head, and I keep moving the head forward, head forward, head forward. So when it prints out, the first item is actually the last item I put in. So I get 5, 4, 3, 2, 1 when I go through this loop right here. And I go for, this is the list current. Current is equal to head. Start at the head. Current doesn't equal null. Current is equal to current next. Next, next, until I hit null. So I'm going to start at the head and go to the end of the list, and I'm going to print out the data that's in it. And we're putting them in. The head is equal to new node. Head is equal to new node. If we do that, we have the head, it's going to be equal to new node, head equal to new node, head is equal to new node. So it keeps going to the left of the list. So we're putting it before the head, which is giving us our, this is why I talked about first in, first out, last in. This is giving us the last one. This is giving us a stack, yeah. So the first one is the last one we're going to take out if we talk about the order of the list. So it goes in descending order. So. Digest. Mellow. I'll leave this one. I'll upload the one with the 5 get characters in there. So we can put those up on the website later. So digest. Think about it a little bit more. So I want to skip this part here and talk a little bit more about pointers, and then come back to this one. So I have another little piece on pointers that I kind of want to go to next. And I believe it's this one. It is this one. So this one is lecture 2, by the way. And what it's going to do is it's going to run through a bunch of different pointer types for us. But now you know what they're used for. They're used for linked lists as one example. They're used to send large amounts of data to functions. Another example. So these are some of the different manipulations that we can do with the pointers. So it holds a memory address, just remember that, and the memory address is to another object. And you can directly manipulate those references through those memory addresses. So we're manipulating those nodes through 2 pointers, a head and a current. And we can have, in that case, we had 5 nodes, all through a head and a current. So we don't have that many pointers. We only create the pointers that we need given the logic that we're trying to work with. And we have unlimited amount of memory. So we have memory issues that might be associated with that if we have indirect issues with losing track of the memory. So pointers are useful for creating linked list data structures such as trees and lists, managing dynamic objects, and they function as parameter types for passing large objects to arrays. So the pointers themselves are associated with types. Just remember that, the employee type, the person type, the integer. The type tells the compiler how much memory contents the reference location needs. You can't take an integer pointer and have it point to a float or have it point to an employee. That's not going to work. You're going to get an error message. So here's some examples. There's a string pointer, a couple of integer pointers. You can declare them the same way. You define them in the same way as you define the other pointers, other variables. We had the reference, the dereference. So example, correct or incorrect? Let's take a look here. So now we're going to refresh our memory and quiz us a little bit here. We have integer variable 1 is equal to 333. Integer variable 2 is equal to 444. Pointer. This is the other reason why people like to put the pointer symbol next to the pointer variable. See, I don't like to do that. I'll do this in 2 separate lines. I'll do integer pointer, and then I'll put pointer value 1, pointer value 2 on a separate line, which, not quite as good because now you can't put them all in the same line. So if you put the pointer symbol next to the name of the variable, then you can do 1, 2, 3, 4 all in one shot. Just showing you. So can pointer variable 1 equal variable 1? No. We actually tried that, and it didn't work. With PTR and myInt, won't work. It's incorrect. But can pointer value 2 be equal to the address of variable 2? Sure, why not? That's the same thing we were looking at. Can pointer variable 1 equal variable 2? Pointer variable? No. P-value 1 equal P-value 2. If an integer is equal to an integer, yes, it can, actually. What about this one here? Integer P-value 1. Isn't it saying the same thing? Yeah, dereference. Oh, there's a pointer here. Yes. It's stuck underneath. I was looking at the text of it going, what? It's dereference pointer 1 is equal to variable 2. Yes, that can be done. And dereference pointer 2 is equal to dereference pointer 1. Yes, it certainly can be done as well. So in terms of our pointers, noticing that the pointer definition of the asterisk is the symbol that indicates the pointer type, and it is not a dereference operator in this case, it's a reference operator. So example here is that we follow this one here and we have it equal to this one here. That makes it equal. Incorrect. During initialization, a pointer can only be assigned an address. So integer variable, this is correct. It can be assigned pointer variable here at the address of variable. So this is an assignment expression. This is an assignment and an expression. This is an assignment, but it's not through an initialization. So it has to be initialized to a variable address, and you can't put a value to it until it's been initialized. Just like if you said integer I is equal to 5, well, you have to say integer pointer is equal to address of something, because it has to be equal to a memory address. So references are also referred to as aliases. That's why we can call a head and a current. Those are aliases to memory locations, and we can use them that way. So it's used as an alternate name for the objects. In most cases, they're used for formal parameters to functions as well. So reference type is defined by following the type specifier in the address of operator. So we have the address of reference variable 1 could be equal to value 1. Which we can actually do it the opposite way as well. Or value 1 might be equal to 333, and the address of it's going to be equal to this one. So references must be initialized. Once defined, a reference cannot be made to a reference to another object type. So if we unless we typecast the object. So if the reference is an employee, it has to be equal to an employee. Unless we take the employee, well, unless we take something else and make it into an employee. So it has to be apples and apples together, just the same way as variables have to be assigned to other variables, unless you cast them. Operations on the references are exactly applied to the object in which the reference is referred to. Here's an example where we have the value 1 is equal to 333, and then the address of the reference value 1 is equal to value 1. Value 1 plus plus, increase it. Value 1 plus equals 100. Well, you can do that. They're all integers. So the operation is valid for the integer type. If you try to run an operation like a string concatenation or something like that on an integer, you're going to have a problem. So only the allowable operations can be applied to the allowable object types. So, and here's a review of the pass by value, pass by reference. So it's called pass by value. Sends a copy of the contents to the actual parameter, so the calling block sends to the function a copy. So the actual parameters can't be changed, but the pass by reference, it sends the actual object. So the object itself, the reference to all of the components inside of the object, are changeable. So it sends the location of the memory address to the actual parameter that's being used, and it changes the actual parameter. So that's a little bit on that as well. And I'll talk a little bit about C strings, because have you seen them so far in the string class? We used string class in the first weekend, and I told you there's a bunch of methods that go along with it, but it didn't talk about the methods. So we know how to use it. We know how to include string. And we know we have different types to initialize the string. So we can say string my string, hello string, string my other string is equal to string. Or we can go string my final string, which is an empty string. So we've seen this so far. I've been using this a lot. But know that you have other ways of initializing the string. You can send it, and if you look at this syntax here, this is an object. You're calling the constructor to construct a string, and you're sending it a string. So the string object has a constructor. This is the default constructor, by the way. Doesn't take on any parameters at all. Just like employee, just like person. Instead of giving it an age every time I sent it, here the string takes on a string. So my string, string. And the string could be a string, or it could be a reference to a string, my string. So know that it is an object and instantiates just like any other ordinary object, and you can run the constructors on the objects. Well, you can also run methods on the objects itself. So the length of the string is returned by a size. So here's myString.size, running a method on an instance of an object that you've created called myString, and myString is right here. And myString was run by the constructor that sent hello folks to the string. So just like any other ordinary object. Which is funny because people teach strings before they teach objects. And then you don't get the connection sometimes, and then you look at that and you go, string is an object. Well, how do you know that? And then you can run all these methods on this string, and you're like, well, what do I mean by that? Well, that's weird. But if you learn objects first, and then you see it in other contexts, and then you look at the string, then you go, oh, well, that makes sense. Like half the people don't know that that's a constructor that's running because they don't see it. So, all right, so we have, you can use an empty operation to find out whether or not the string is empty. So Boolean is empty. If string empty is going to be equal to my string empty, because empty is going to come back with true or false. It's a Boolean method that says Boolean empty, return true or false, depending upon whether or not it's empty. You can use the equality operator to check whether two strings are equal. If my string is equal to my other string, well, the strings are equal. How can you do that? If the objects are equal, you can do it with an employee. If employee Bob is equal to employee Barb, if all the data matches itself, then they're equal. So you can do it. You can copy one string to another string by going my final string is equal to my other string. Same thing you can do with an operator, a copy. You can use a plus operator for concatenation. So you can say string 1 is wow, string 2 is ouch. Constant character, which is equivalent to a string actually. It's a pointer. S3 is yuck. And you put them all together, you say string 2 is plus equal to all this other stuff, and you print out string 2, S2. You get ouch, wow, yuck, ouch, whatever. So we have another topic to discuss here is the constant type qualifier. You put the keyword constant at the end of a method, you can't change anything inside a method. So we've seen that in a couple examples, but just to give you some more. You can transform an object into a constant by putting it before. So constant double pi 3.14, when are you ever change pi? You're not going to. The data type is double. You put it at the beginning constant, makes it so you can't change it. Which is kind of interesting because when people start putting it on everything, it's like, well, what if you want to change it? Then you can't change it. It's constant. And then they go, how come it's not being updated? Because you made it constant. Because they downloaded it and copied it from some source code example they found online. And it had said constant everywhere. Use it. Don't use it. Don't use it unless you know what you're doing with it. Constant allows you to store parameters in well-defined places in your code, have them associated with a type. They must be initialized, otherwise you can't assign a value to it. You have to initialize it. This is the initialization right here when you say equals something. Constants cannot be modified after their definition, and they replace the define. So we shouldn't see any defines in your code. Constants replaced the defines technique that was in C. So, constant qualifier, sometimes you want to define an object as sets or states of actions. As an example, you can define the following states for counselor: observe student, shout at student, follow student, recharge batteries, and you can have constant states. So you have constant state observe students is equal to 1, shout at students is equal to 2, follow students 3, battery 4. And then you can have a function for robot states that can be defined as a Boolean set robot state, and then check the states and then return the states. That's a lot of variables. So if you want to make better use of all these variables, in C++ and C we have enumerations. Don't have these in Java. And we don't have these in other languages. And we have them in Objective-C. Enum. Enum, we have them in Java now. Okay, in the earlier versions of Java we never had enum. So, yeah. Actually, you're right. I wasn't thinking about that. But in the most current versions we do have. And originally we never had enumerations, which is kind of interesting. It's mapping states. So the 0, 1, 2, 3 is mapped to a name, and you use the name instead of the 0, 1, 2, 3. Because what does 0 mean? Don't know. It's a bunch of colors. What's 0, 1, and 2? I don't know, red, white, blue? So you cannot restrain the range, the values that have been passed to it. So there's no useful typing for that. So enumerations type, put one together here. We have an enumerations, enum. Are you sure Java's got it? Yeah? Okay. More current versions of it then. Older versions never had it. I had to go online and look up to see what version it was that implemented it. But this is strictly a C++ thing, or C dialect. Comes from C, it's used in C++ all the time. So is type define, which we don't have in Java. Well, unless they added that too. So. JavaScript has type. JavaScript has enumerations. I just don't think Java's got enumerations. Does? Okay. Enumeration types can be defined as this here. We got robot state, observe student 1, shout student 2, whatever. And we set the numbering at 1 instead of 0 with this. Otherwise, we start with 0. Just like an array. We're going to cover array after we take a break in a few minutes. But this way we define new type robot state that can only be assumed to have 4 different values to it. And the values are actually these words here instead of 0, 1, 2, 3, 4. Because these words make more sense, which is why we're enumerating. We're enumerating the 1 to be equal to observe student and the 2's to shout at student and stuff like that. So the values still correspond to integers. So you could say cout follow student gives you the output of 3. Follow student? Yeah, follow student. Recharge battery. This is robot. I guess the robot's following the student. So if you're able to restrain the values by passing the robot state to 4 legal values, we can use it as a value for the parameters robot state space new state. So we're going to send a state to each one of the robots. So, and this is the Boolean we're going to run for it. So robot state current state is equal to new state, return execution successful. Any attempt to call the robot state with an integer value or a value that's different from the enumeration will cause an error message. So safer than using integer values because you're limiting it to only the ones that are defined for the enumeration. We already talked about structures, but if you're still not familiar with the concept of structures, see Lecture 2 starting at slide number 42. And it goes through the entire concept of structures. We saw structures, we also saw unions. I want to skip to the union because that seems to be causing some people some issues. I have one slide on unions coming up here. Structures, just like a class, it holds multiple pieces of data all together, all in one name. And then we can make different data types. We can actually put a structure inside of a structure, just the same way as we can put a class inside of a structure. We can put a structure inside of a class as well. So the union is a structure that holds only one of its members at any time during execution. So here's our weight type, as I was trying to mention before. A long, an integer, and a float, only one of them it can be allocated. So there's only one space being held for the union. And they're all being held together. So at one moment in time, you might have ounces, pounds, or tons, but you're not going to have all three simultaneously per structure, or per union. But you could have different unions. And in each one of the union holds a float, the other union holds a double, the other union holds an integer, and all the unions could be equal. They're all the same data type. So it takes one data type and transforms them in a kind of a non-object oriented way, creates a polymorphic union where you can have one of those three types. So here's an example union weight type, and then we have weight type weight declared as a union. We could say weight in tons is equal to 4.83, weight in pounds is equal to 35, and so we end up with the ability to store different values for the different weights. And at any one moment of time we could have more than one union and they're all storing the different data types that might be associated with it. So I'm going to end this actually because I think we have attendance that's going to start right here. So when we come back we'll take a look. We're going to take a short break after the attendance, and then when we come back we're going to take a look at arrays next. So